Okay. Okay, so we have the great pleasure of having a presentation by Antonio Celani. Antonio received his PhD in physics for the Politecnico di Torino and was a postdoctoral fellow at the University di Torino and also the Max Planck Institute for Plasma Physics in Germany. And he is currently a research scientist at the ICTP. Previously, he held positions as Directeur de Recherche in l'Institut Pasteur and Chargé de Recherche in CNRS, also in the Institut Non-Linéaire de Nice, in France. And he was a Poincaré Fellow at the Observatoire de Côte d'Azur, Nice, also in France. So he's interested in a lot of very, very interesting things, such as statistic fluid dynamics, stochastic control, and thermodynamics, and navigation and reinforcement learning. We are very eager to hear his presentation about learning to navigate in dynamic environments. The title of his presentation is Learning to Soar Like a Bird. So if that title is not interesting to you, I don't know what can I do, because for me it is very much. So thank you a lot, Antonio, for coming and giving us this presentation, and please, whenever you like. Thank you.
Thank you very much for having me here. Thank you also for making me feel so old by listing all my previous appointments, but I think that's fair. So it's a pleasure to present to you my a part of my research activity over the past few years. The original title of the talk was Learning to Navigate in Dynamic Environments, which is, I think, a more encompassing title for what I do. But here today I will spend my time on one specific example of an organism who is able to perform extraordinary feats in a dynamic environment, which is the atmosphere. And in the end, I will very briefly tell you about other different lines of research that I pursue, which fall inside this bigger or maybe under this bigger umbrella of navigating dynamical environments. So another question that might come to your mind is, so what wasn't this school and supposed to be about machine learning? Yes, so my talk will be about machine learning eventually, but it starts out with biology. And this is also one thing that is I think it's something I'm very keen about. That is the connection between animal behavior and machine behavior. And also I think that it should be clear to you all by now, as you're progressing into the school, that most of the concepts of machine learning didn't come out of the blue or simple in the minds of a computer scientist, but are much inspired by biological response and biological behavior. So you can think about connections between vision and computer vision and deep learning. And so the kind of machine learning that I will explore here is called reinforcement learning. So I will give you a few highlights about what it is. And you can think about it basically as the algorithmic language for behavior. Okay. And what kind of behavior are we interested in here? Well, it's inspired by a very, very simple and I think quite widespread observation. That is, I think all of you have seen that there are certain birds, certain species of birds, which have a very large wingspan, like for instance condors that you can see depicted here. And these birds are able to stay up in the air for very long times without flapping their wings. Okay, so they can glide, they can even soar, so they can use the kinetic energy of the fluid environment in order to lift themselves up in the air, basically with little or no effort. Okay, so this is a very striking behavior. You can see it in humble birds like the seagulls, or in more royal birds like the condor, but it's something which is very widespread. So this is an interesting biological behavior per se, in the sense that we might be asking, so how do they do it? So what kind of things they measure about the atmosphere? What can they know? How can they predict where they have to glide, in which direction they have to go in order to exploit the conditions of the atmosphere? So these are all plausible and interesting biological questions which can be addressed by ethologists, that is, biologists who are interested in behavior, or neuroscientists, or engineers when they think about how the flight is actually operated. But then it's easy to realize that for any kind of this behavior, there is a robotic counterpart. So in this case, you may think about gliders, which I hope I can change slides here. Please. Okay, right. So you should see here the picture of a glider, which is a plane, it's also called sailplane, which has a wingspan which is very large, could be in the 20 or more meters. It's very slender, as you can see. In this case, it's operated by a human, which is sitting in the pit here. These gliders are actually able to do extraordinary performances. They can fly for hundreds of miles without the use of any thrust. Okay, so the overall reasoning that I will try to follow is just to try to think about these two different problems, the biological one and the engineering robotics one, as just one single problem. Try to distill a general understanding of how these animals and machines can use the atmosphere to extract power and thrust for their travel, and then sort of try to give a unified picture in terms of reinforcement learning, that is the machine learning language. Okay, so I think we are ready to start. So these are my main collaborators in this work. So this project has originated already some 5 years ago, when Massimo Professor and myself were at Institut Pasteur, and then along the way we have had the precious help and substantial contributions of Gautam mostly, and then also by Terry Sejnowski, which is one of the founding fathers of machine learning, and also by Jérôme, who did a lot of work on the robotics side. All right, so soaring, as you see here, it's a seagull. You can see it can stay up in the air or even go up without flapping its wing, and it's a phenomenon which is so apparent and conspicuous that it attracted the interest of Lord Rayleigh already 150 years ago, almost. And Lord Rayleigh was already able to sort of characterize different ways about how this soaring works. And there are several actual sources of energy that in the atmosphere that the bird can exploit in order to soar, that is to go up in the air. We will be interested in mostly in one of them, is that when there is convection in the atmosphere, that is when the air is hotter close to the ground than it is above the ground, then the atmospheric flow becomes unstable, and there are regions of space where there are hot air columns which raise and cold air columns which go down. And so locating these hot air columns, which are called thermals in the jargon, is key to be able to extract kinetic energy from the atmosphere and turn it into potential energy. So if you wish, in physical terms, you can think of birds as very, very effective thermodynamic engines, which are able to extract energy from an environment which looks noisy, because everything is very turbulent, so fluctuations are unpredictable. So it looks like it's like extracting energy from a thermal bath. It is not the case, of course, because turbulence is not a thermal bath. It's a strongly out of equilibrium system, and therefore there is the possibility of extracting energy from it and put it to work, and therefore gain height in this process. Okay, so I forgot to say at the beginning that I am totally happy if you have burning questions and you interrupt me on the way, or otherwise, of course, I will answer questions at the end. But if you feel like you're really stuck, don't hesitate to interrupt me. Okay, so how do birds do this? So you can see here a peregrine falcon. So this is a bird which is able to soar for long distances. It has received here you see there is a log attached to it, so we can measure many things, including the trajectory that it makes. And this is here is a sample trajectory taken over several hours, and you will see these patterns of circling about, spiraling up. Okay, so in red here, reddish color, you can see that there is a vertical velocity component. So they go up, circling with this soaring process. So you can see an enlargement of that on the right hand side, and then they can just let themselves go and use the vantage position to launch themselves on a prey, which they do with exceptional speed and ability. And then if they miss the target, they can engage again in another sequence of spiraling behaviors, so on and so forth. And they can do that for several hours in a sunny afternoon by exploiting these thermals, and with a very little energetic expenditure. So there are even more striking examples of how to exploit energy from the turbulent environment. So this is an example of Frigatebirds, which are migrating birds. They every year they make a long migratory route starting from southeast of Africa and going to Southeast Asia. So they cross the Indian Ocean. It takes for them about a month or so, and they travel a lot. Every day they cover about 300 kilometers. And then by logging the trajectories of this and also physiological parameters of these birds, the researchers were able to show that they also engage in this cyclic pattern of soaring by means of thermals, and then letting themselves down at the base of another thermal. And this takes them basically to expend energy in flapping their wings just 10% of the time. So basically what they do is that since they have to eat and they approach the water, they eat some fish, and then they take off. And in this part of the day where they eat and take off from the sea level, they flap their wings, but otherwise they don't do that. Okay, so it's very impressive. It's an incredibly impressive performance. And more recently, there has been also another paper which I want to cite here. Also, condors. So this might be geographically even more interesting to you. The Andean condor, a group of researchers led by Sergio Lambertucci, who is an Argentinian ethologist, has shown that the Andean condor can soar for 100 miles without flapping the wings. So this is really something which brings their ability to the limits, to the physical limits of performance. And the Andean condor, I beg you to notice, is very heavy. Okay, so there's an exceptional gain in energy that these birds are able to achieve. Okay, so this was basically our motivating examples. So obviously the questions that arise is, how do they do it? So what does that mean in practice? How do they do it? Well, they need to measure something about the environment, right? So there has to be some flow of information from the environment, from the physical environment to their brains. And this information that comes in, which of course we can suspect it's partly of visual origin, partly of sensory motor origin, okay? So there are something, and also they can measure things about the environment, like perhaps wind speeds or wind accelerations. So they have an array of sensors on their body that allow them to perceive the local state of the environment. Of course, these input has to be turned down into an output, okay, which is this information has to be mapped into a sequence of maneuvers. So what should they do? They should bend on one side. They should change their position relative to the wind. So how is the algorithm working that maps this information into decisions? So do they use a model of the environment? So are they able to sort of forecast the local meteorology for a few seconds, for a few minutes? So are they able to forecast for an hour what will be the weather situation in order to decide where to go? So all these questions are open questions, and we are still not, I mean, as a community, the ethology community is not able yet to answer to all these questions. But nevertheless, this is essentially the key question that you have to ask whenever you talk about behavior. Okay, so what is sensed by the animal or the machine, and how these sensations are turned into decisions. Okay. Okay, so in a nutshell, the good news is that there is already a mathematical language which provides a framework to talk about decision making in a precise mathematical way. Okay, and here I will give you a very, very brief crash course about reinforcement learning. Of course, this will definitely fall short of conveying you all the relevant messages, but I hope you can catch the idea, the gist of this approach. So the reinforcement learning idea is basically that there is an agent, okay, a decision maker, and there is an environment, and there is a loop, a continuous loop of information which is flowing from the agent to the environment and vice versa. So the agent acts, makes decisions which turn into actions, and these actions produce changes in the relative situation of the agent with respect to the environment. And then the environment in turn gives back to the agent percepts, which are the sensorial inputs to the agent. And in reinforcement learning, these percepts are separated into two components. One is the so-called observations. Observations are contextual observation. That is, they provide information about the context. Okay, and rewards are signals which tell the agent if it's doing well or not with respect to a given goal. Okay, so the underlying idea of reinforcement learning is to provide mathematical language for goal-oriented behavior. So behavior which has an aim, which has a well-specified goal which has to be attained. And these rewards are the elements that sum up in making up the objective. Okay, so all of this was, of course, very, very abstract, because this language is meant to be very powerful to describe a variety of decision-making processes. But how do these abstract objects, which I'm talking about, are to be interpreted in our particular specific problem at hand? Okay, so clearly in our case the agent is the bird or the sailplane. Okay, that's the place where decisions are made, and these decisions are the controls. Okay, so how can the position of the bird or the glider change in the course of time? Of course, birds and gliders are very complex objects. They can change the position of the wings in many ways, or on a sailplane you can have flaps, you can have ailerons, a lot of variety of controls. But in the following we will simplify this range of operation controls to a minimum. Okay, so now this is a part of the talk where I usually do a lot of acting, in the sense that I show by moving my hands how to interpret the meaning of what I'm talking about. So I'm sorry you will be missing that, or maybe it's good for you, I don't know. But anyway, I will try to convey the idea. So basically, as for any objects which we might consider rigid, it's described in space by three angles, the three Euler angles. And basically, so there are 3 degrees of freedom which can be controlled. here we will be focusing only on one specific kind of control, which is called the roll. What is the roll? The roll is the ability of a plane, if you want to think of a plane, to rotate along its main longitudinal axis. Okay, so these are rotations. So the plane is bending to the left or bending to the right. So we will assume in the following, to make things as simple as possible in building up our model of a flying agent, that it can only control the roll, that is by bending, or as it's called in the literature, this is called also the bank angle. Banking means that you are moving on one side, okay? And as a result, this will make the bird or the sailplane turn to that particular side. Okay, so we will ignore other kinds of control for simplicity. So what is the environment in this case? Well, how does the agent relate to the environment? Well, it's of course very important its position. So what is its height? What is its position? Its posture with respect to the environment, and also what is the state of the atmosphere. So this is an enormous space of possible states. Okay, so you should have to specify pressure and temperature and wind in every possible position which is relevant for the decision making of the bird, and then all possible degrees of freedoms of the bird and freedom of the bird, and then the height and distance from the ground, properties of the ground. Of course, all of this is not accessible to the bird. Okay, and it could be more accessible to the sailplane, but we will consider, again, in the spirit of making a minimal model, we will consider the minimum amount of input that can be given to the decision maker. So we will just focus ourselves on situations where our bird, virtual bird, okay, does not have any visual information. So we are playing with a toy model of a bird which is blind, and it's also very, very, very poor at flying because it can only bank on one side or another. And the only thing that it can sense is its own relative position and its own accelerations. So this is a very simple set of inputs that come from the environment and that the bird is aware of. And we only assume that basically it knows if it's going head down or head up or banking on the left or on the right, and whether the wind is accelerating it upwards or downwards. Okay, so these are very simple measurements which actually can be done. If you think on the robotic side, these are things that can be measured by a simple smartphone. Okay, it's not high-tech measurements that you want to consider. Of course, birds are much better than that. Sailplanes are much better than that. But the goal here is to show that if you are able to make such a simple model of a bird learn to soar, then clearly there's room for doing much better in reality. Okay, so what is the reward in this meaning? Well, the reward here is the immediate gain in height. Okay, so if the bird goes up a bit, then it's we sort of give a reward in the sense that it's an encouragement. It's a form of reinforcement. Okay, so every time that the behavior is going in the right direction, there will be a reinforcement to enhance that kind of behavior and reduce the frequency of other behaviors. That's the essence of reinforcement learning. Of course, when the bird gets too close to the ground, then we give a penalty. Okay, so the idea is to construct these structures of rewards and punishments so that when the bird is interacting, virtual bird is interacting with the environment, he will be able to learn how to convert these inputs into decisions that maximize the distance that it can travel upwards, okay, for simplicity. So the total goal will be to maximize the long-term gain in height. Of course, this is just one part of the task, because on the long term, the bird also wants to go from one position to another. So there will be a part where it has to decide to leave this thermal and then glide back to the base of another thermal. But let's not focus on that for the sake of simplicity. And just let's consider the task that the bird has to identify where the thermal is and exploit it to the maximum. Okay. Let me control time. Okay, right. And then the goal of reinforcement learning is to identify a policy that is a mapping of observations into decisions that maximizes the goal. Okay. So how does reinforcement learning work in practice? Well, I will take another few minutes in order to show you that the actual algorithms that are the basis of reinforcement learning are quite intuitive, even though they can be technically demanding to implement in complex situations. So the basic idea is that you build up a table, which is called this Q function here. And this table depends on the states of the environment, or at least on the percepts that you can have on the environment, and the actions that you can take. And this table basically is meant to contain how much you expect to obtain as a total reward over time if you adopt a certain strategy. And so the basic idea of reinforcement learning, so this is the table. So you look at an item for a given state. So that basically for the bird, this would be, if I am at a certain given angle with the horizontal and with the wind, what should I do? Should I bank to the right? Should I bank to the left? Should I stay where I am? So these are the actions and these are the states. So the algorithm, basically what it does is that it continuously updates this estimate of the of how much you can get in the future by behaving in a certain way, and at the same time improving the decision. Okay, so it's an algorithm which basically corrects itself. So at the beginning, the bird will take random actions. It doesn't know how to map its sensations into decisions, so it goes about at random. But then some decisions turn out to be bad, and some others turn out to be good. So at the next round, the bird will start making more of good decisions and less of bad decisions, and that's what this algorithm does. Okay, so I will have to skip about all the math, but you can trust me that this is something which has a very, very solid foundations in the theory of Markov decision processes, and of course I could speak for hours about this, but that's not something I'm going to do for now. So what we did first is to train virtual birds. Okay, so to create a virtual environment by means of a numerical simulation of a chunk of the atmosphere. So we ran direct numerical simulations of a cube by 1 kilometer side with a resolution of 1 meter. And this was basically simulated. So these are snapshots, but you can imagine that there is a very dynamical situation in which you see that there are structures of vertical velocities and downward velocity. And we integrated this for a physical time of about 15 minutes. So this 15 minutes time scale is very important because this is a typical lifetime of one of these vertical structures. So in 15 minutes, if you had something going up here, hot air going up here, after 15 minutes, very likely there would be a negative downfall. There is cold air going down, or maybe hot air going up, but basically the correlation is totally lost over a time scale of 15 minutes. And this is interesting because if you plug in the typical soaring velocities, the vertical velocities of soaring birds, in 15 minutes they can go up exactly by 1 kilometer. So you see that it's a task which is particularly complicated because these structures that they have to identify and exploit have the same lifetime of the task that they have to do. So they have really to be able to catch the occasion on the fly. Sorry for the pun. Okay, so this is very highly dynamic and unpredictable environment, and as you can imagine, it's a very difficult task. So we did this on the computer, and at the beginning we started with the naive birds. That is, our virtual birds do not have any specified policy. They do things at random. So by repeated trials, they have to. Sorry, I'm looking at the chat. Okay, the punk was gonna, yeah. You have to learn both how to fly and how to identify where the thermal is. And then the good news is that even in this very simplified model for the flying bird, and with a very standard off-the-shelf algorithm, we were able to see an increase in performance as they learn from, just focus on the red curve here. So this is the beginning of the learning process. An episode is a chunk of duration of 15 minutes. And so you can see that after 1,000 episodes, more or less, they already leveled out to a performance of about 100 meters. Okay, so it's not quantitatively close to what a real bird can do, but you can clearly see that they have learned to do something. Okay, and so this was very promising to us. Of course, there's a lot of that I can tell you about how these birds do this. So what kind of autopilot they use in order to perform in this way. But in the interest of time, I will have to skip this. Maybe I can get back to this if there are questions like this. But what I want to do now in my remaining 10 minutes is to discuss the application of these ideas to the realm of robotics. So like I told you in the beginning, sailplanes are beautiful machines for gliding and for soaring. So just to give you an idea of the performances, they can fly at hundreds of kilometers per hour. In one afternoon, they can cover 2,000 kilometers if it's a sunny day, and they can go up to 12 kilometers. And all of this without ever spending a single gallon of fuel. So the kind of trajectories that these sailplanes do is actually very similar to the ones that birds do, actually. So they go up in this, so for some reason in these races, they plot graphs in the opposite direction. So it starts away from the finish and it arrives here. But you can see there is this alternance of rising in place trajectories, which are these spiraling up for hundreds of meters. Then they let themselves fall down to the base of another thermal, and so on and so forth. And pilots do this by a series of empirical rules, empirical knowledge, experience, visual cues, okay, which is a very, very sophisticated behavior. And the question is, would it ever be possible to replace the pilot's experience with some algorithm, which, just like the one that we use to train birds, would be able to drive these vehicles without having man on board? Of course, this has several possible applications, from long-haul delivery, but also to deploy medicines or any kind of safety equipment in regions where you don't want really to deploy people. Okay, so there are lots of possible applications in this sense. So the big question here is, can we build an artificial intelligence system for autonomous soaring? So I want to point out that this is not much of a technological challenge, because this kind of vehicles already exist. Okay, so these are hybrid vehicles which use solar power to generate thrust. They also have a aerodynamic shape which allow them to fly without thrust. They are small. Okay, so these are just I think 5-meter wingspan. But unfortunately, one of these toys is in the 10,000 euros. So they are not really very affordable if you want to experience yourself how to train a glider. So we were doing something less ambitious, and we use these toy gliders. So these are actually recreational toy gliders. They have a 2 meters wingspan. They are used by people who just want to have fun with them. So they are equipped with a motor. They can be controlled with a remote control from the ground. The motor can be switched off. They already come with a series of sensors on top of them. So they have accelerometers, they have pressure sensors, and they cost just from a couple $100 to $500, which is much more reasonable expense, since we were projecting of crashing a lot of them. Turned out that we just crashed one, which is probably the thing we are most proud about in all this work. And so the idea was to deploy these gliders in an open field and see whether the glider was able to learn online how to ride the thermals and how to go up in the air. Now, when you go from a virtual situation, that is a simulation in silico, to the harsh reality, well, there are several problems that you have to face. So the first problem is that you cannot fly wherever you like. Okay, you cannot fly a drone, you cannot fly a glider in every position you like. So often you have to take a car and drive 30 or 40 miles before you get to a place where you can drive. And then the second thing is that the atmospheric conditions are not always the ones that you want, because in order to have convection, that is, in order to have sufficient hot air ballooning up, it has to be a sunny day. And so this reduces a lot the number of opportunities in which you can train your glider. So when you do a back of the envelope calculation and you say, okay, I expect my glider to learn in about 1,000 episodes. Well, in human terms, this takes months, if not years. And then your nicest postdocs or PhD students will tell you, I'm not sure I want to do this over the next year. Okay, and that's a perfectly reasonable answer. But this has motivated us to sort of try to understand how to do the learning better. Okay, because when you want to train a robot, you really want to push the ability of learning to the maximum in order to be able to do as many physical trials as possible in the shortest possible time. So on top of this important conceptual challenge, there are all sorts of other engineering challenges. I mean, a real plane doesn't behave like the toy aerodynamics that we used in the simulations. It can have vibrations, it can have all sorts of weird instabilities if you don't drive it properly. So it's really a challenge in itself. But let's forget about this second engineering part, which was, of course, very painful for our students, but they have done this courageously. The bottom line is that we were able to train this glider in just a few weeks, and eventually it was able to develop a strategy that enabled it to substantially perform rather well with respect to a naive hardwire strategy that we could implement. So we were rather happy about this finding, but even more happy we were when we realized that if you take a look at the strategy that our glider has been discovering, well, you can plot it in this very simple way. So this is a table basically in which the abscissae and the ordinates represent the current state of the glider. So basically, how is it bending on one side, which is this mu angle, or how much acceleration, vertical acceleration, is it perceiving, which are the red symbols here on the ordinates, or how much torque is it experiencing? It's been torque on the left, on the right, or no torque, neutral torque. So, and you can at every instant of time, the sensor will tell you in which of these slots you are. And then when you are in a certain slot, this will tell you what to do. So if there is a blue arrow, this means you will have increased your bank angle from 15 to 30. Okay, if you're here, then you go back. And if there's a square, you say, don't do anything, stay as you are. So this is how you read the autopilot in practice. And we were delighted to discover that if you look carefully into this diagram, you realize that it's just an algorithmic description of a set of rules which are well known to the professional sailplane pilots, and they go under the name of Reichmann rules. Okay, So this sort of ability of recapitulating, at least qualitatively, because of course there are also quantitative differences, because these are working for a sailplane which has a 20-meter wingspan, whereas we are working with an object which has a 2-meter wingspan. Okay, so there are some differences in the figures, but still, nevertheless, there is a substantial correspondence between the qualitative content of these rules and the qualitative description of our strategy. Okay, so let's wrap up with the questions, because as it always happens, we end up with more questions than answers. Is this strategy really what birds are doing when they fly? We don't know, but this is certainly something that we can ask biologists, because we are sort of pointing the finger in the direction of certain particular observables, which might be tweaked upon by neurologists or by biologists. So maybe they can take inspiration from these questions and look from our perspective into birds soaring. Then, like I told you, this is just one tiny bit of the complex navigation scheme that birds have to do. And we haven't addressed at all, for now, the problem of how to leave a terminal and catch up the new one. This requires more learning. This requires more strategies and probably more observables and more actions to be taken. And of course, there's a general problem that we've been handpicking the kind of observables. So we decided, let's assume that our bird is able to measure accelerations, is able to measure torques, but there might well be different observables. Maybe a combination of pressure and temperature is the key to very good performance. How do we know what is the good performance? So this is something which still is an outstanding question. And also from the methodological viewpoint, how do you look for this kind of observables in a machine learning approach? And then birds usually don't fly alone. Okay, and in particular, birds like condors or griffons, which are very good soaring birds, they use the experience of other birds. They look at each other. Sometimes they imitate behavior, sometimes they do different things. So multi-agent navigation in dynamic environments is an extremely interesting subject, which we hope we can further work on the future. Then last slide, there's a whole variety of problems which have to do with animal behavior, from microscopic to macroscopic, from mechanical sensing, like the one I've described here, to olfactory sensing, because odors are also carried by the atmosphere, and therefore the olfactory landscape of insects and birds is highly dynamical and unpredictable. But nevertheless, we know that birds and insects are able to do extraordinary search tasks based on olfaction. So all these kind of problems go under the umbrella of learning how to navigate and make decisions in dynamic environments, and I hope I had your interest on this subject. And with that, I'm done, and I'm happy to take any questions if there are.
Thank you, Antonio. It was really amazing talk. I feel like I want to learn how to fly a glider now. I was always very afraid of these things, because you are afraid that you don't have any active propulsion, but now you have convinced me that it's not as difficult, or that's the issue, to say the least. Do you fly, by the way? Or
I was offered to fly on a delta wing with a professional, but I declined.
Okay. I don't blame you. I would probably have done the same thing. So while we wait for questions, I have, okay, so there is one question. So in real life, okay, so we have many questions silently, so I'm coming in.
Okay, I can read them, and I can read them loud and then answer.
Yes.
Okay, so in real life, are there different contexts or context changes that may generate different policies? Is the learning robust to such contexts? Okay, that's an excellent question. There are different levels of changing or variability in the environment. So the one that we are looking in this case is sort of, if you wish, meteorological variability. So what happens over the course of minutes to hours? And our policy is, by definition, is robust with respect to these meteorological changes. But you're perfectly true if you think on the other side to more climatological situations. So, for instance, we have been training our birds in a particular specific location, which is in the outskirts of San Diego. So it's one place. But now suppose that you want to train this in Northern California, or in Washington State. Of course, the environment is going to be different. The typical situation will be different. So you will have, in a sense, to retrain your bird, because the policy will be different if the sort of climatological conditions are different. So how do animals and machines cope with this kind of problems? Okay, so this is a very interesting, more general subject, which is the subject of transfer learning. So how do you transfer your knowledge in a specific setting to another setting, which is probably related, but not necessarily the same? So this is an extremely open and interesting subject for research in itself. There are some things which are easily transferable. So our birds or gliders did two things. So first they learned how to fly, so not to fall. And then they learned how to soar. So we expect that this ability of keeping up the flight will be easily transferred to another environment. Whereas the strategy for locating thermals where they are will be changing from one side to the other. So one possibility is that if you train in a series of, say, 4 or 5 typical climatological situations, you can compile a series of 3 or 4 tables. And then what the bird will do is first assess in which of this situation it is, and then use the appropriate policy. Okay, so you can sort of build up a hierarchical structure in which there are policies which are learned, and then there is a sort of master coordinator which chooses which of these policies are appropriate to the environment. So I hope that this addresses your question, but that's absolutely a very good point. The second question: in gaming agents like AlphaGo or FastStar, is there arrived at new strategies that are not human strategies? Have you observed something like that? Okay, excellent point. So I think we are observing still subhuman strategies, in the sense that our virtual birds or gliders do still have a performance which is definitely lower than the one of birds, because they, like I said, we didn't emphasize the ability of extracting proper observables, etc. So I definitely can state that for our work, we are absolutely on the lower side of the spectrum, something very, very simple, very, very basic, which, however, may have the benefit of being robust. But of course, I mean, if you train enough your glider in the proper conditions with the proper machine learning apparatus, so using deep learning to extract observables, using computer vision to detect the situation of the atmosphere, I expect that you could easily surpass the performances of professional pilots. As for birds, they have been spending a lot of time with evolution, so might be a harder challenge. Okay, did the training suffer from overfitting? Okay, so in our case, overfitting was not on the map, simply because we chose a priori a very, very coarse-grained space of states. So our actual number of variables is very small. Our Q matrix is described by something in the order of 60 parameters. So overfitting would arise if you took the approach, for instance, of fitting your observations into a deep learning algorithm and then to extract decisions on the basis of that. That's how top reinforcement learning algorithm, like the ones that you use for AlphaStar or for AlphaGo, they work this way. So they have very powerful convolutional neural networks in front. They do suffer from overfitting, and that they do use regularization. We need not to do it because we basically, so we as physical modelers, so we think we understand something about the phenomenon. So we choose some observables, that is, we use our prior knowledge as modelers, and this is the sort of the strongest regularization that you can do. Okay, if you want to think of that in that sense.
There was a previous question, I think, by Cynthia about the weight.
Sorry,
and the role. Yes.
Okay. Do you think that could be applicable to help in the navigation of more robust airplanes, or the weight is crucial? Okay. So drones are absolutely on the map. Actually, there are already many works on applications of reinforcement learning for drones flight, especially multiple navigation by multiple drones. So that's certainly on the roadmap. For more general airplanes, I mean, I think you understand, just like jets or airplanes with thrust, there is no obstacle whatsoever in that direction. Even though, of course, as you correctly point out, the dynamic is shifted, because the role of gliding in planes is much less than the one in sailplanes. So it would be a different physical problem, and then you also have sort of a more complex trade-off between the human intervention, as you can easily imagine, and the automated pilot. Most of the commercial flights now are basically 100% automated, but of course, as you can imagine, there are I think there is less room for exploration in that direction. But yes, certainly interesting.
So I have a question myself. So in the reinforcement learning model, you have basically the policies are in reaction to the instantaneous measurements of, I don't know, the different variables. But is it possible that you can also introduce some sort of memory or integration over time? And this is something that you might be missing, that perhaps the birds are doing, but the model isn't doing? Absolutely.
That's an excellent question. So the kind of approach we took is exactly the one that you say. We chose what is technically called as a reactive policy. So the actions are taken reacting to the current observation. Of course, if you use the memory of all observations, so if you had a record of all the observations and decisions that were made in the past, of course, this would improve a lot your ability to perform. But there is a trade-off, because if you have to rely your decision on a string of observations in the past, also you need exponentially more learning, because you have to associate to all possible histories some decisions. So there is a trade-off. There is a tension between having algorithms which are too simple, that is, they use too little states, too little observations, too little memory, but they are easy to train, and algorithms which use a large observation space, long memories, but that are more difficult to train. So one has to always identify the sweet spot where one can achieve quick learning with the maximum possible benefit from the observations.
Right. So we have Hermanis. This is a question of differential programming.
Differential programming. Could you give me something more? I'm not sure about. Okay. Well, I'm sorry. I'm not familiar with that. At least on the basis of just the name. Let me quickly have a look. If I'm. Okay.
So it seems like an optimization, continuous optimization.
Okay. Yeah. I know what class of problem is this. I was not familiar with the particular problem at hand. but this falls into the class of situations where you basically do the learning while constructing a model of what will happen in the future. So we have not been doing this. We've been using a model-free approach. That is, everything is based on experience, and there's no attempt at constructing any kind of forecast in the future. Of course, if you have this ability, like in this class of problems that it seems to suggest, then you can exploit it to its best and try to forecast and therefore optimize better. So we haven't done that, but that's certainly a very interesting suggestion. Thank you.
I have one final very short question. Is, do you think this? I can think of other similar problems, and I was like, when you're talking about gliding, I was thinking that, for example, sailing could be a similar problem. Like, in the sense you don't have any active propulsion, and you're reacting to the turbulent non-equilibrium potentially environment. So do you think this could also be applied to, for example, sailing? And
absolutely, absolutely. Sailing is certainly another example of where it's a control problem in a strongly dynamic environment. We are not working on that. One thing that we are currently working on is related to sailing, which is kites. Okay, so using kites to extract energy from the atmosphere. This is the current project we are undertaking. So how to use kites to move stuff around or to produce energy by using turbines or generators. We are very much interested in this because it's a clean way of generating energy. It's not very expensive. It's light. I mean, it's not heavy. So it's not just like windmills. And you can deploy it also in developing countries because this is always something which is of our concern. We as ICTP are always very much interested in what is relevant for developing countries. So this is a way of combining basically our understanding of biological behavior and trying to export it into tasks that might be relevant for developing countries.
Okay, well, I think that's all. And really, I have to really thank you because it was really a wonderful talk. I mean, it really got me thinking a lot of things. And I think also all the students have the same impression. So thanks a lot for making some time to present your talk, and hope, well, we can see around when this COVID situation is over, we might meet in some occasion in person. Thank you a lot, Antonio.
Thanks again.
Thanks, it was a pleasure.
Thank you, everybody, and stay safe.
Thanks a lot. Bueno, we're moving to the next